In this video, I'm going to cover the basics of regression mechanics, basically kind of what we know of as line fitting. And I want to show a little bit more detail about what a fitted regression line does. And the emphasis in this video is to do this through several very structured examples, so I can highlight very precisely what's happening when we fit a regression. This is a really practical topic. This is a type of thing that you see show up in popular press. So I think you're going to find that like some of the examples and so the idea of line fitting is going to be sensible. But I want to take in this video the extra step of showing precisely what kind of underlies this. So we're going to open the hood a bit to sort of think about this. We're going to start with a very simple example from my YouTube channel, and then we'll kind of use that to kind of launch into kind of a more general discussion of what line fitting is all about. Then we'll do kind of a more organic example with some birds data that you worked with on perhaps the last homework if you're in my MS class. And then I'm going to show an illustration in Excel which highlights this from kind of a different perspective. So think about this as sort of three different perspectives on the same thing. Our goal is to kind of understand the mechanics of regression. So let's begin with the first example. So what I've done for this first example is I have a data set of 5 videos that I've recently recorded on my YouTube channel, and I just I grabbed some data on these 5 videos. In particular, their video length in number of seconds and the number of views that these videos have. There are a lot of other characteristics that can determine sort of how much people view a video, but this gives you a sense of the exercise. And I want to think about the relationship, however, between views and video length, and I want to think about that relationship in the context of fitting a regression line. So that's you can see the data here. Here's one observation for one video. It had a length of 1,091 seconds, and number of views was 61, and so on and so forth. You can kind of see the 5 different observations here. Okay, so that's the underlying data set. I have that stored in the Active Directory. I've already kind of gone through the script to make sure that sort of everything works. So I've already set the Active Directory. If you're going to sort of download this and kind of go along with the example, you can kind of do the same thing by saving the file in your Active Directory, or navigating session, set working directory, choose directory, and find the directory where your data are stored. So what we'll do once that's the case, once you're in your Active Directory, it simply just reads the data in. Good practice to just take a look, see if the data actually read in, worked like a charm here, and so that's nice. And then I'm just going to show kind of what the plot looks like of the relationship between views and video length. A plotting function has a couple of different modes. This is one mode that I like. It sort of thinks of the views variable as the sort of the outcome variable or the response variable, and it thinks of video length as the x variable. So it's y tilde x. You give it a formula, you tell it which data set to look for the variables with those names, and then I just want to plot these as diamonds, so PCH equals 18. You can kind of do your standard plotting if you'd like instead. And so you can see if you do this plot, you get what's called a scatter plot that relates video views to video length. And eyeballing it, there seems to be kind of a weak, moderate negative relationship between views and video length. Not saying that longer videos cause fewer people to view, but just just an association between these two things. And so that's, I mean, just sort of looking at a scatter plot, you kind of get that kind of information. What we'd like to do in regression is actually be really precise, and more precise in that we'd like to fit a straight line to this relationship so that we can sort of more accurately say, well, as we increase the video length by, say, 1 second, how much would my prediction of video views decline? That's kind of the exercise in sort of estimating a regression line, is to try to find the line that sort of fits this relationship the best, accounting for the fact that, well, there's some noise. You're not going to be able to, if you have more than 2 points, fit this relationship perfectly. And so the line is going to miss. But we want to reduce, sort of pick the line that misses by the least amount. So what does that mean? Well, I wrote a function, and this is kind of in the background. In the script I'll upload, I'll have all the details. But for this illustration, I just wanted to show, well, what does this fitted line look like relative to the points that it's intended to fit. So you can see this is actually the best fitting line. And I've sort of illustrated how it does relative to each of the 5 video observations. First thing to note is the line does not go through any of the points. It kind of sacrifices perfect fit on one of them for sort of better fit, being closer to some of the all of the other observations. So how is it actually doing this? Well, what we do is we consider lines on the basis of, well, how far is sort of each observation. If I just put kind of a random line on this graph, I could sort of draw this vertical line from each point, either down in the case of this observation here, or up in the case of this observation here, which is below the line, either down or up to the line. The length of this line segment is called the residual. It's sort of the amount by which the line misses that particular observation. Each observation in your data set will have a residual, and it's a measure of it's an observation-specific measure of sort of the lack of fit. Better fit would have smaller residuals, and collectively we want these residuals to be small. And so what does the best fitting line do? What it does is it takes each of these residuals, it squares them so that they're all positive numbers, and adds them up, and then picks the line that minimizes that sum of squared residuals. That's mechanically what's going on underneath this, underneath the hood of regression. So if that kind of gives you an idea of what this fitted line does, well, we sort of, that's kind of the process by which we pick this fitted line. You can see that if you do kind of enough of these plots, that fitted line has like a lot of nice properties. You know, it feels like it sort of penalizes really bad lack of fit worse. It tends to deliver a fitted line that really actually maps closely to the relationship in the data. So that's kind of what we're doing in this example. Now, something else to kind of point out is kind of under the hood, what did my function do? Well, my function actually computed, well, what was the prediction for each of these observations? So for that first observation, our best prediction was that it was going to have 56.7 views based on sort of that best fitted line. How then would we compute the residual, this sort of vertical distance between the regression line and the point? Well, all we do is we just say, here I'd like to create a new variable, call it the resid. That new variable I'm just going to take as the difference between the y variable, so what is the height of that point, so vids views, so 61 in the case of the first observation, and then I just subtract off the prediction. That gives this notion of, well, Now, what then are the various residuals, right? And so the residual for the first observation was 4. For the second observation, it was 4.07. For this one, it was -9. For that one, it was 11. This one was -10. Something to sort of point out is if you add up the residuals, you get 0. This is mechanical. If the residuals didn't add up to 0, what could we do to the fitted line? Well, we could just kind of shift it. If the residuals added up to a positive number, that means that we're kind of over or under predicting the points on average. And if we just kind of move the regression line upward, that will fit them better. There's kind of another kind of restriction. We'll talk about it once we get to the slides. Is that the sort of the covariance between, or really correlation between the residuals and the views, or sorry, not the views, the x variable video length, that also equals 0. You can see that's very sort of tiny number at rounds to 0. And so those two restrictions actually are things that sort of happen with any regression. And it's sort of useful to have those two restrictions in mind when working with kind of regression output and transforming it for other purposes. So those are some things to kind of keep in mind when thinking about regression. Now, I'd like to talk a little bit about this conceptually before we then do another example. And what we just did in that example is there's one way to think about it, is we decomposed the data, each observation, into a part that was the fit, that is this sort of line that we could then think about that as kind of having this kind of common component, and then the part that was lack of fit, the residual. And for each observation, for any candidate line that we kind of put on that plot, we can compute residuals for sort of each of the observations that we're considering. Each observation has this residual. It's that vertical distance between the fitted line and the sample point. And our goal in regression is to make those as small as possible. So here, if you think about sort of squaring each residual, we denote a residual as lowercase e, and then observation number is the subscript. Square each residual and we add them up, gives us what's called the sum of squared errors, or sum of squared residuals. It's called SSE for sum of squared errors. And if you minimize that sum of squared residuals, what that gives you is gives you the regression line. Now you might ask yourself, well, why square instead of just taking the absolute value? Actually, both are perfectly fine. It turns out that this is what's called the minimum absolute deviation. It's a perfectly fine objective to use, but it's not as common. It's a little bit harder to use. There's several reasons for this. One is that it requires more computational power because sort of finding a minimum of a sort of absolute value function, there's kind of a kink there, and so you have to use different methods. The other is that it's not as directly related to correlation, which we've talked about in the class, and as kind of a more intuitive measure of sort of how things are related. As we'll see, regression and correlation have a really tight relationship to one another, and so we'll want to sort of be able to say, okay, here's how we can then think about how correlation relates to sort of our regression coefficient, like the slope of this regression line. There's going to be a direct link between those two things. Furthermore, sometimes you want to penalize bad mistakes or sort of bad misfit on an observation worse than not so bad misfit. And so it turns out that if you take the absolute value, well, that kind of treats like same kind of like making a bigger error on like an already big error at the same as making like that same like sort of type of error on a smaller residual. This minimum absolute deviation puts kind of less weight on the bad mistakes. whereas in sort of the standard least squares, sort of minimizing the sum of squared errors regression line, you penalize bad mistakes worse. And so that's just a feature of the fitted line. When we minimize the sum of squared errors, it turns out that we get sort of nice equations for what's the slope and what's the intercept of the best fitted line in terms of just what the data give us. So it turns out that when we were back here in R, and we looked at this, how did it fit this regression line? Well, it actually just used a formula for the solution to the fitted line from the sort of what given the data. It didn't actually minimize the sum of squared errors, even though that's what it did. It used this formula, but this formula actually implies sort of minimizing the sum of squared errors. So what is the formula? It turns out that the slope of this regression line is fully, you can compute it as the covariance between x and y. We've talked about covariance quite a bit recently, divided by the variance of x. So if y is the vertical axis variable views and x is the horizontal axis video length, this is just how you can compute the slope of the regression line. If you want to compute the intercept, there's kind of a handy trick that if you were to look at our regression line back here, turns out that this regression line, along with every other sort of fitted regression line, goes through the mean of x and the mean of y. So if you were to compute the mean of x and the mean of y, the regression line actually goes through sort of the middle of the scatter plot. Let me just actually kind of illustrate that. So if you were to go have AB line vertical, let's see, and I want to compute the mean of vid length, I'm just going to plot this in red. You get a vertical line at the mean, and then we can do a horizontal line at the mean of views. And you can see that there, here we'll just kind of zoom in on this. The regression line actually does meet this point. If you kind of look at where the regression line, it's not an accident that the regression line actually goes through this point, sort of x bar and y bar. Sort of using that fact, we can kind of come back to the slides. We can basically just figure out that, y bar. What does it mean for the regression line to go through x bar and y bar? It means that y bar equals the intercept plus the slope times x bar. You just kind of add the slope times x bar to both sides. And then to get a solution for what the intercept is just going to be the y bar minus the slope times x bar. So these are just features of the data set that we can use. Covariance between x and y divided by the variance of x. That gives you the slope. And the intercept is just this sort of involving the means and sort of using this trick that all regression lines go through that kind of pivoting point, x bar, y bar. That's actually, aside from being sort of a useful algebraic trick to figure out what the formula for the intercept is, it's actually going to be useful for thinking about when we have problems with particular observations, and we'll return to that fact that there's this anchoring point for regression lines to go through the mean of y and x. So just sort of looking at this formula for covariance and variance, we could actually re-express this in terms of correlations and standard deviations. The trick is that covariance equals the correlation between x and y times the standard deviations of x and the standard deviation of y. The variance is just the standard deviation of x squared. So if you kind of write that out and then cancel one of those standard deviations, you get another sort of nice factor here that the slope of this regression line, which we denote as beta 1 hat, that equals the correlation between x and y times the standard deviation of y divided by the standard deviation of x. So we have a couple of different ways to compute this depending on which information we have available to us. Now, one note about notation. I've been using some notation that sort of indicates that the slope and the intercept are going to be statistics that estimate population parameters. We'll return to that kind of in a later part of the class, but the book might use some notation of like lowercase b is the estimated slope rather than beta 1 hat. But these really are just the same thing. We're just sort of saying a little bit more about the estimated slope, that it actually estimates the population parameter that we think of as the true relationship between x and y. Same for estimated intercepts, so sometimes you'll see it as lowercase b sub 0, or you'll see it as beta hat sub 0. So this just a little notational comment. Maybe I should have mentioned it when I was sort of saying, well, here's the slope and here's the intercept, but sort of useful to sort of see different notations for the same thing, because sort of in reality you're going to see all sorts of different notations for these things. You just have to sort of adapt to the situation. A little bit more about this. Here are those two conditions that I showed in the context of our specific example. One is that the average residual is 0, or that the sum of the residuals are 0. Those two are basically the same statement. That just has to be the case, otherwise the regression line can be shifted kind of up versus down. The other is that the correlation between x and the residuals, the x variable in the residuals, is 0. If it wasn't 0, then we could tilt the regression line differently. So the way you can think about this is the average residual is 0. This kind of pins down kind of the height of the regression line, where the intercept is, and the correlation helps pin down, well, where's the appropriate slope. If kind of one of these conditions is not set equal to 0, then you wouldn't have a line that fits as well as possible. There's another reason why these things hold. This is a minimization problem. We're minimizing the sum of squared errors, which is just a function, but a function of the intercept and the slope for the line that we're choosing. This is a sort of a multivariate optimization, but what you effectively do is you take the derivative and you set that equal to 0 to find kind of the minimum of this function. When you do that, well, there are two first order conditions, and that's what these basically boil down to. I'm not going to go into kind of more detail about that because it doesn't provide more intuition for what we're going to do, but these conditions, sort of knowing that these hold, is useful for kind of other properties. There are two other things, two other useful properties about the fitted regression line. One is that we can think of the regression as this decomposition between the fit and the residual. Not just sort of that sort of y equals fit plus residual, but also in terms of the variance of the variables as well. So what we can do is we can then think about when we think about a regression. It turns out that if you just use that the sort of form for a regression, it's just y equals beta 1 times x plus e. The fitted, or sort of y equals the intercept plus the slope times the x plus the residual. If you just kind of use rules of linear combinations, you get this really nice variance decomposition. There's the part that the regression line explains, sort of how much of the variance in y is explained by x. That's just going to be the coefficient on x squared times the variance of x sort of follows that that kind of formula that we have for linear combinations. And then the residual part is just the variance of the residuals, and that's the part of y that is unexplained by x. From this variance decomposition, we can get sort of a common statistic to report about regressions that tells us sort of how well we fit. Namely, we just take the ratio of how much we were able to explain using the regression to sort of how much variance there was to explain. That is what's called R squared. And it's called the coefficient of determination, if you're looking for sort of another thing to call it. But this is simply the fraction of variation in y explained by its linear relationship to x. And R squared has this formula, but it's also useful to know that R squared is the correlation squared. So R in the R squared actually relates back to computing the correlation. So you can see correlation actually plays a really important role in regression. It sort of tells us sort of more than just like is this strong or weak relationship between the two variables. If you square a correlation, say the correlation is 0.7, you square that, you get 0.49. It tells you that 49% of the variation in y is explained by its linear relationship to the variable x, and that gives you a nice quantitative way to describe sort of how much variation is explained. Now, this has a lot of applications. It's not kind of an end-all be-all for regression. We don't necessarily seek regressions that have greater R squared. It just is a good descriptor of, well, how much variation does the regression line explain. So we've gone through a fair number of formulas. It's going to be useful to actually apply them and show you how to sort of implement regression within R. I want to do this with a kind of an interesting example of a data set on bird-to-air collisions. So our textbook has this package called OI data, and you can install it within R. I believe most of you already did that for your most recent homework, but if you haven't installed this, the script here illustrates you can install the packages. It'll install the dependency packages. If you have already installed it, you still do need to sort of load the library of functions. And the thing that we're looking for here is a data set that's stored within this library called birds. And the way we can read this in from the library is that we just use the function data on birds, and it reads the data in. So this wasn't read in externally from like another file. It was stored within a package, and this can sometimes be, you can have some interesting example data sets. I find this data set particularly interesting, mostly because it exists. It's a data set on the height, speed, and characteristics of birds and planes that come into collision with one another. So we're going to do something that's a little bit weird. We're going to look at, well, what's the relationship between the height at which the bird and the plane came into contact and the speed at which the aircraft was going. And so we can get a sense for, like, aircraft is going really fast, that bird is pretty much doomed, and where essentially get some idea of what this relationship looks like. So you can here I've got some code that plots all these bird-aircraft collisions. Unfortunately, there are a lot of them in this data set, but you can see here's height in feet, kind of incredible. This observation corresponds to a bird-aircraft collision where the bird was over 25,000 feet and the plane was going about 400 miles per hour. I can't imagine that bird survived. I don't know what the bird was doing so high, but it gives you an idea of, like, you're not really, when you're cruising at an altitude of 25,000 feet, very unlikely that a plane's going to hit a bird. When you're on the ground, it's actually pretty likely, especially when you're sort of taxiing or taking off. These planes get going pretty fast. there are quite a few observations here at 0, 0, where the plane is just sitting there and the bird whaps it, or the bird gets sucked up into the engine, and these things have to get reported for maintenance purposes. It's a data set that's useful for the airline industry to avoid costs, but like you can kind of get a sense of kind of what these bird airplane collisions look like, looking at the speed versus the height of the collision. Sort of makes sense that this would be upward sloping. Higher is the airplane, so the faster it's likely to be going, and so there's kind of a downward sloping or upward sloping relationship between these two. This line just overlays the best fitting regression line. You can see the best fitting regression line. It's got to compete it's got to account for like the sort of the density of the observations and how well it's fitting those. Looks like it's really trying hard to fit the observations that are sort of in the bulk of the data at these sort of lower altitudes. But it's also trying to account for these observations that where it's not doing a great job fitting out here, where it's sort of over predicting the speed at impact based on that linear relationship to height. One thing that this points out is that maybe the relationship isn't linear, but a regression model, that's all you have, is you have this sort of linear relationship between these two variables. So if this is the best fit line, it might not be the best fitting relationship that we can sort of put in there. But it's sort of useful to sort of point out that look, there's some lack of fit here. It's systematically the case that these observations that are at really high elevations are going to be kind of over predicted. They're going to have negative residuals, and so that's something just to note about this, the way that this fits. So let's just kind of get into the data set. Well, let's try to compute the correlation. And what you'll notice is that this returns an NA. This data set's real data, and sometimes it has some missing information. And the missing information, you just know that the bird hit the airplane, but you didn't know like how fast you were going, or maybe you knew how fast you were going, but you didn't know what height you were. So like there's some missing. For like standard deviation and for mean, you just go like NARM equals true, but like there's a problem here is that there might be some missing for height that aren't missing for speed and vice versa. So there's actually a different option for the correlation function. It just works a little bit differently. What you do is you say use equals complete observations. That is that you want sort of the observations where you have both height and speed, you want to use the correlation for just those observations. Compute this correlation. It's reasonably strong, 0.68. If you square that, you get kind of a moderately large number. Well, I was going to square it without kind of moving on, but you square it, you get 0.464. That means 46.4% of the variation in speed at impact is explained by the linear relationship between speed at impact and the height of the bird plane collision. That's a pretty strong relationship. Sort of indicates that about half of the variation is not explained, but it's a significant amount of variation that's explained between these two. Now, let's kind of step through those calculations to sort of compute like what's the intercept and what's the slope of this regression line, just applying those formulas that we had before. Now, to alleviate the issue of having missings and having to do this use complete observations, well, let's just what I'd like to do is drop any observations for which we don't have complete data. There's this function called complete.cases that applies to a data set, and it gives you sort of true if you have full information on the data, and false if not. And if you give a data set true falses in the row column, what it can do is it'll just drop any of the observations. You'll see our number of observations went down to 12,161 from something like 19,000. So we had quite a few missing bits of information. Just didn't know when the bird hit. You just saw the dent and the evidence that there was a collision, and so it still needed to be reported to the data set. Seems like that happens actually fairly frequently. But for the observations for which we have information about this relationship between speed and height, well, let's compute this regression line. So okay, here you can compute R. I didn't want to use just the letter R because maybe that's taken. So I just wanted, so that's our sample correlation. Here we can compute R squared, and just to verify that what we did by dropping the data and then just computing it without the use complete, we ended up getting the same thing that we had before. For our calculations, particularly for the intercept, and we'll need the means, the mean speed and height. We're going to store this in x bar SP for the mean of speed and x bar HT for the mean of height. We're also going to need the standard deviations of height and speed. And so if you want to compute the slope, well, we had two options if you remember back on the slides. So we had two options to compute the slope. One is we could compute the sample covariance, divide by the variance. The other is we could compute the sample correlation and then multiply by the ratio of standard deviation of y, standard deviation of x. Well, let's go ahead and sort of do each of those and show that they work the same way. So we're going to do the second one first. Correlation times standard deviation of speed, that's our y variable, divided by the standard deviation of height, that's our x variable. Compute that, we get our B1 or beta 1 hat. B1, we get a slope of 0.016. Now, what does that mean? It's got a very tangible meaning. What this means is for every increase of height of 1 foot of the bird-airplane collision, as x increases by 1, my prediction via the regression line for speed at impact increases by this number. That's how you interpret a slope. It's I go over 1, how much do I go up? That's the slope. And so the way we interpret this, so in context, would be as height increases by 1 foot, my prediction for the speed at impact increases by 0.016 miles per hour. Well, if you don't like the 1 foot and 0.016, you can rescale this by multiplying both of these numbers. So let's say at 100 feet would kind of give us a more sensible sort of interpretation. So as the height increases by 100 feet, I get 1.06 or 0.016 times 100, that'd be 1.62 additional miles per hour. It kind of gives you a sense of sort of how the speed increases on average when we think about the changes in the x variable. Well, here's kind of an alternative way to compute the same thing. More just showing, look, if you compute the covariance, divide by the variance, you get the same thing as if you compute the correlation and multiply by the ratio of standard deviations. It should be the same thing. Those are equations for the same thing. It's just depends on the information that you have that's different. Now, if you want to compute the intercept, well, you get the mean of y minus the slope times the mean of x. I call both of these x bar because they're both sample means, but I guess I could have called the speed one y bar, but I wanted to name it speed. That is our y variable, so really that's y bar minus the slope times x bar. That gives us the slope, and that's so you can see there's our intercept. Intercept's at about 121. Looks like it's about 100, but here's actually where 0 is, so that's at 121. Well, just to kind of verify, well, let's use the canned regression function to see what that gives us. That gives us both the intercept and the slope. The intercept is labeled as such, And the slope it's not labeled as slope, but it's labeled as the name of the variable that on which we have the slope. It's something to keep in mind when you're interpreting regression output, is that it won't say this is a slope, but when you estimate a regression, well, that's what you're estimating. That coefficient on height is the slope on height. Kind of cool that it matches exactly what we had here, just kind of different significant digits than because it's kind of going through this function. Something that we do in practice is we'll estimate the regression. I'll sort of point out this function is called LM instead of regression. LM means linear model, and in statistics, like there's some like other ways to like fit things that aren't linear, and so they call it LM instead of reg. But that's just the convention in R. How is the syntax? Just y tilde x, and then you tell it in which data set do you look for y and x. This gives us the sort of the regression output. Now, here we can get we can also just store the regression. It turns out that it creates what's called a regression object or an LM object, and you can do all sorts of kind of interesting things like plotting the regression. Here I'll just kind of show you. You get like these kind of plots, and we'll actually spend more time in the course kind of going through like what do these plots tell us. But like that's actually going to be kind of the next segment after we discuss statistical inference for regression, is like how do we think about these diagnostic plots. But you know, this gives you a wealth of information stored in this regression object. You can, from the regression, compute the fitted residuals. Here's for every observation how the regression did. You can show a histogram of the residuals. Well, that's a little weird. Why is that weird? Well, I didn't do my par MF row to get back to one panel. Just do the histogram of the residuals. You can see kind of what the residuals look like. If you just want the coefficients from the regression, you can extract those using this coef command, and that's actually what I was doing earlier when I wanted to plot the line. If you want what the standard regression table, this gives you even more, including things called like a standard error for the intercept and a standard error for the slope. Now, thinking back to our inference unit, when we had an estimate for a parameter, we knew that estimate would vary from sample to sample, and that we'd want to quantify how much it would vary from sample to sample. Well, this standard error gives us that for the intercept of the regression. And this standard error gives us that for the slope of the regression. We're going to spend more time with that later, but it's just kind of worth noting that all of that is kind of stored in here. So, main point for this video is just the kind of how the mechanics of this works. How do we get this fitted line? What does it mean to fit a regression line? And some of these formulas, you know, the correlation times the standard deviation of y divided by the standard deviation of x, that gives you the regression coefficient. The slope coefficient, that's a useful thing to kind of have in mind. Now, this is a very R-based way of thinking about it. Returning to our outline, sort of what have we done so far? Well, I showed a very simple example with video views, just 5 observations. We went through some formulas for the slope and the intercept, and then we did this example in R with the birds data. I want to conclude the video with kind of a different perspective on what a regression line does. And this is, again, just kind of reinforcing some of the mechanics of regression. What I'd like to do is I'd like to relate the returns for a fund. I gathered data on this and sort of put it into Excel. Returns of a fund to the returns on the market. I'd like to find kind of the best fitting line to give that. What we can do is we can say, well, okay, here, if I wanted to get the sort of the best fitting line, it's really quite straightforward in just applying the formulas. You just compute the correlation between the fund and the market. You multiply it by the standard deviation of the fund. That's going to be our y variable in this case. We're predicting the fund's returns based off of the market. divided by the standard deviation of the market, and that gives us the slope of the regression line. If we want to get the intercept, just go the average of y, it's the average of the fund returns, times the slope, which was stored just next to it here in H9, times the average of x, and then that gives us the slope. Quite simply just gives us the slope and the intercept for these two things. Part of what I want to show you is that those formulas, fairly easy to implement. They're just formulas that you can apply. But I want to show that if you want to actually minimize the sum of squared residuals, that you end up getting the same thing. So how do we compute a residual? Well, you could sort of imagine, let's posit that the line actually has an intercept of 0 and a slope of 1. This is wrong, but you can, for that line, compute the residuals for each observation. So here you can see there's here's the fund return. That's going to be minus the intercept minus the slope times the market return. Actually, another way to put this would be, well, minus the intercept, really actually minus the equation for the regression line. Intercept, so here's the fund return. That's kind of the thing that we're trying to predict. And then we just kind of subtract the sort of the measure of fit. So here's the intercept plus the slope times the value of the market for that observation. Now, what I want to point out is if I just kind of copy this down, it doesn't quite maintain what I'd like to do. You can see that these two cells migrate down, but these two do as well. It's kind of nice that I'd like to actually have the red one and the purple one just kind of stay back where they were instead of that happening. So what you can actually do is you can use an Excel trick where you put a $sign in front of the row, and the row stays put. And if you copy that down, just kind of dragging that corner, you can see that you basically maintain that same equation regardless of sort of how far you copied it down. I can do this and copy it down farther. You can see here I'm still going kind of the fund return minus basically what the regression line would be telling me. So here I can just drag this all the way down for all of the data that I have for this example, and that gives me the residuals for each observation. Notice R was doing this kind of in the background, or you can think about R could have been doing this in the background where it computed the residual for sort of each observation, just applied this sort of function based on like what the intercept and the slope were. Here, now if you want the square of the residuals, just the next step in computing the sum of squared errors, well, you just square that residual that's in the column next to it. So I can just copy this, Control C, kind of do my trick of going to the end of that and then coming back up, and just kind of copy it over here into column E. You can see there, column E now has all of the residuals, and this sort of cell here in I4 just adds up this column of squared residuals. So what argument I made at the outset was that the regression with these formulas minimizes the sum of squared residuals. One thing I could point out is you can kind of change what's the intercept, and that gives you a different SSE. If you change the slope, that gives you a different SSE, and so on. What I want to show you is that if you have your solver add in Excel, hoping you can do that sort of on your own time, what we can do is we can say, well, let's take this SSE, and I'd like to minimize it. But I'd like to minimize it by changing the slope and the intercept. What this tells Excel is try out a bunch of slopes and intercepts until you find the one that makes the sum of squared errors the smallest. That's the same thing as sort of minimizing the sum of squared errors, and it's not doing calculus, but it's using Excel's solver to do this. We go ahead and click that, so tell it to solve. We keep the solver solution. You can see I've got sort of a different thing that popped up. And what do you know? We get a number that's very, very similar to what we had in our regression. So here, let's kind of boil this down to like the same number of, what is that in scientific notation? Let's make this, we want a smaller number of significant digits. And make this smaller number of significant digits. You can see that it's the same as what we had there, right? So like this would round to 0.0001. This one is the same as kind of what we had there. It's off by a little bit. I think that might be kind of numerical error. So let's kind of try a different starting point. You may sometimes have to do that with when you do solver. And so here we'll pick kind of the SSE. We'll tell it to minimize using those. Tell it to solve. And you can see there it sort of more closely nails it. Part of what's happening in this example is that the residuals are so small that the kind of numerical optimization gets a little bit kludgy. So if you kind of find that like your fractional you have data that in very small numbers, sometimes it can be useful to have your data in percentages instead of fractions for returns, for example. Just because for like the numerical optimization, it might not work quite as well. Now, the part of the point of this is that it's nice that we don't have to do the numerical optimization, so we have to sort of kludge our way through things. Like going back to these regression formulas, I mean, there's no numerical optimization here. Like that is the slope of the regression line that minimizes the sum of squared errors. Hope this example kind of shows that like when you minimize the sum of squared errors, like we just did here with Excel Solver, that delivers you the same answer as just applying the formulas that we have available to us. So thanks for following along with this video. I hope it's helpful and fills in some of the gaps that we've had for our snow adventures. We'll see you all in class.